Excellent. Okay, so welcome back. So before Christmas, we got up to understanding what a weak derivative is and understanding why it is that you need continuity between elements in order to be able to take derivatives in the normal sense that we understand taking derivatives in finite element. What we're going to do now is we're going to spend this lecture actually understanding how you build finite elements. So what the maths is of making the finite element spaces. And later on in this lecture, we'll sort of dabble our toe in that case for two-dimensional elements. And the three-dimensional case is very similar to the two-dimensional case. And that will enable us to come back in future lectures and start actually building finite element problems in more dimensions and working out how we solve them. So in order to do that, we need to go back and do a little bit of theory again. So if you remember way back at the very first lecture of this course, which we unhelpfully numbered lecture -1, we talked about vector spaces, and we talked about the fact that you can have a vector space whose elements are functions. And so now we need to take this a little bit further, and we need to talk about what are called dual spaces. So if you already know what a dual space is, I apologize. I'm going to take this fairly slowly because it is a slightly mind-bending concept when you bump into it for the first time, and you need to understand this in order to understand how nodes work. So if we remember, a vector space is simply a set on which we have an addition operation and a multiply by a scalar operation, and those operations kind of behave the way that we think they ought to. So in particular, so we had a long list, which I will reiterate now, of what all those properties were. So I'm going to, like last time, use Greek letters for the scalars and Roman letters for the vectors. So if we have our set V, which is a vector space, then alpha x is in V, where x is any vector in V and alpha is any scalar. So for scalar, we understand for the purposes of these lectures a real number. Right? You can have complex value vector spaces, but we're not concerned with those. And similarly, if I take any two vectors and I add them up, then I get a vector in the same space. I need commutativity, which means that the sum of two vectors is the same no matter which way I do the sum. Oopsies, not times. Plus y. That's completely hopeless. Let's try that again. X plus y is equal to y plus x. I need associativity and addition on the same thing, which means it doesn't matter what order I do the additions in. So x plus y plus z gives me the same answer as if I do the z addition first. So that's x plus y plus z. And I get the similar rules for the scalars. So it has to be the case that alpha times beta times x. So that's where I've done them from left to right. Alternatively, we could think of doing that. That's got to be the same as alpha times beta times x. So that's a slightly less obvious operation, right? So if these were just scalars that you're multiplying, then that would be blindingly obvious. But remember that that thing, that's a scalar multiplication, and then I apply the scalar multiplication to my vector. Whereas in this case, I've scaled the vector to get a new vector, and then I scale the new vector. And this is saying that they have to be the same. That has to not be the same thing. Similarly, we have distribution law, so that means that if I have the sum of two scalars multiplied by a vector, that's the same as alpha x plus beta x. Distributing works the other way around as well. So remember, I've got two addition operations. I have addition of scalars and addition of vectors. So that one says that addition of scalars distributes. It's also the case that alpha of x plus y equals alpha x plus alpha y. So we also distribute over addition of vectors. The zero vector has to be in the space. So that means there exists 0 in V such that x plus 0 always equals x, any x in the space. And similarly, if I take 1, which is the multiplicative identity in the scalars, then it always has to be the case that 1x equals x. So that's the whole list. And we demonstrated last time that you can have a vector, well, we knew that you can have a vector space whose members are discrete vectors in Rn. That's the obvious case that you were thinking of first. We demonstrated previously that you can have a vector space whose vectors are functions, and we proved everything that we did about finite element using those properties. So now I want to look at a new class of functions that are kind of interesting. So the functions we've considered so far were functions from some domain in Rn to Rm. Those are the, so we have a domain in space, so one-dimensional domain, a two-dimensional domain, a three-dimensional domain, and a function in this space associates with each point in the domain a value from Rm. So in the scalar case, m is 1, right? So no matter what, so I can have a two-dimensional space here and get scalars out here. I can have a two-dimensional space here and get vectors out here, vectors of any length, right? There's no rule that says that just because I'm one-dimensional here, I can't have three-dimensional vectors here. All of those work. Normally, the interesting cases are where m is either 1 or equal to n, right? Those are the ones that come up most. But actually, there are other cases. So if we have an immersed manifold, so the surface of a sphere, then the domain might really be two-dimensional, but we can still think of having three-dimensional vectors because you can have a vector that comes out of the sphere. So that all those cases matter. So that's what we think of as V, right? So V is the set of these functions. So I should say that things in V do this. So now we're going to introduce the concept of a functional. And what a functional is a function from some space onto the reals, R1 in this case, that are real value functionals. And the case that we're interested in are functions which for reasons that will become obvious, I'm going to call this space V star, and things which are in V star map from V to the reals. So let's think about what that means. That means you give me a function and I give you back a real number. So this is kind of like a higher order function, right? It's a function which takes a function and gives us a number back. So all the Haskell programmers in the room should be happy at this moment. And the reason I've called this space V star, so this space is called the dual space to V, right? The space, specifically the space of all continuous linear functionals. So if we restrict that V has to be linear, the space of all, so such that V is linear, the space of all of linear functionals on here, and you need continuous or respectively bounded, whichever one you prefer, they're the same, gets you this one. So that, if you haven't seen it before, is kind of a weird and new concept. So it's useful if we have some examples of things that could be linear functionals. And so possibly the easiest one is that we can integrate the function, right? So if I take f of v is defined to be the integral over the domain of v dx. So clearly, that's a real number, right? If I take a function and I integrate it over the domain, I get a number out. That's what integration does. I wanted it to be linear. That's fine. Integration is a linear operator, right? If I take alpha times f of v, that's equal to alpha here, which is also equal to alpha here. So therefore, that would be equal to f of alpha of v. The same thing would be true if I added up two functions. Integration is a perfectly linear operator. So life is just great. So that's good, because we start to look like we're in territory that we are familiar with and understand. It's also the case that you can expand this in the usual way. So I can, for suitable functions phi, I can say that f phi is a function which takes v's and multiplies them by phi and integrates. That's also a linear operator. It also gives me a number. That's also perfectly good functional. Now I can do something else which we saw a little bit of in the integration class last time and discarded because as a function it wasn't allowed. I can do point evaluation. So I could say that I'm going to have a function fx of v which is defined to be v evaluated at x. So point evaluation, straight point evaluation works like that if this function is a function onto onto R1, sorry. Right? Because I need it to be the case that this thing is a number. If this was a function into Rm, then an example of a functional which is sort of similar is I could have a functional of some position and a direction, and I could say that this is the directional component of that. So that would be a number. This would be in the case where v maps into Rn where n is not 1. So so that's kind of fun and interesting. So if you were paying attention last time and you have an engineering degree, you will recognize that that thing is the dual of the delta function. And as we described last time, there are lots of problems with considering delta to be a function, but it turns out there are no problems at all with considering it to be a functional. That works just great. There's no problems there at all, because that's bounded, linear, everything about it is. And so the reason why you get into trouble when you start considering it as a function is that the typical way that you would make it into a function is by defining this right-hand side in terms of an integral. And there's not really a integral in the normal sense of the word that defines the right-hand side, but that's fine. I didn't need there to be an integral there. So another example that's quite similar to point evaluation that gives you an example of functionals is if I have, what are we going to call this? We can call this delta f xn of v, which is the gradient of v evaluated at a point x in the direction n. So remember, when I take a gradient in general in Rn space, a gradient is a vector, it has a direction. So if I want a number out, I have to choose the direction I want the gradient in. But the gradient evaluated at that point is a number. And the other question we had to ask ourselves in all of these cases is it linear? Well, yes, the derivative operation is a linear operation, just like the integral one is. So if I take the derivative of something times v, then I get something times derivative of v. If I take the derivative of v plus w, I get the derivative of v plus the derivative of w. So that's all of that is good news and works. And similarly for point evaluation, that works fine. You have to remember, so there's a slight subtlety going on here. X is fixed, right? So when I choose point evaluation as a functional, the point at which I evaluate is part of the function. It's not an argument to the function. The argument to the function is which function do I evaluate at that point. So remember, these are functionals. They're functions which take in functions as their argument, not the point. And so so the reason why you might be worried about whether this is a linear operator is that V definitely in general is not a linear operator, right? No one said that V has to be linear at all. V could be x squared. That's absolutely fine. And so the thing that will be worrying you is that it's definitely not generally the case that Vx plus Vy equals V of x plus y. Right? That is not generally the case. But that's not what I need. Right? Because this is a statement about whether f is linear, not about whether v is linear. So the linearity statements for f, so you can combine linearity into one statement, so we'll do that. Say that alpha f of v plus w equals alpha, equals f alpha v plus f alpha w. Right? That's the way that you combine together the two statements that get you linearity. And why is that true?
So such that V star is linear, right?
Sorry?
Such that V star is linear.
V star is assumed to be linear.
Okay, because you wrote.
Oh, yeah. Sorry, yes. So here, yeah, that's very important. The V star is linear. No assumption about linearity of the things in there. Right? So we've already seen that the space of quadratic polynomials over Rn is a perfectly good vector space, right? So that could be the quadratic polynomials, and they're definitely not linear. So what does this mean? This means that the left-hand side is alpha times the function v plus w evaluated at x. And the right-hand side is the function alpha v evaluated at x, and plus alpha w evaluated at x.
The line above needs little subscripts on the f, right?
Yeah, these are. And so now we are just back to the fact that V is a vector space, right? So using the properties that V is a vector space, we know that all that's true. So actually I didn't need, so I made that a bit more concrete by putting in the particular case of what this was, but actually that was true in general, right? That's what it means for this to be the dual space, that would work out and fall out. So the direct consequence of that is that the dual space of a vector space, of a function space, is itself a function space. Right, so all of those properties that apply to functions in here, so the fact that you can add them and you can multiply them by a scalar and all the normal rules apply, that necessarily also applies to V star. And actually it turns out in a bit of deeper maths that we're not going to do here, called the Rhys representation theorem. It turns out that in important ways, the V star and V are very intimately linked. So they're isomorphic is the term. So there's a sense in which they actually just look like each other. And if you want to prove some slightly more advanced things about function spaces than we're going to prove in this course, then that turns up.
Is V star always a functional set?
That's what this statement says.
Okay, yeah.
V star is a set of functions from B to R such that V star is linear.
Okay.
And so a functional is a linear function which takes a linear functional. So there are circumstances in which you might talk about non-linear functions, but for our purposes, they're always going to be linear. Is a function which takes in a member of a vector space in general, but the interesting one is it takes in a function. And importantly, what makes it a functional is the fact that it maps to the scalar space. So it maps to R, or respectively to the complexes if you're doing complex analysis. But for our purposes, it maps always into R, not into Rm, not into another vector space, into R. So functionals play the role in all of our analysis of turning things back into numbers. It's the significant difference. Whereas other functions turn things into, well, whatever. Things in Rm, for example. Okay, so this enables us to actually write down something about what a finite element is. So we needed that. The reason we took that fairly long excursion off into norms was in order to work out what a finite element actually is. And so this is a definition from way back in 1978. By Chiale, or however you're supposed to pronounce that, French mathematician. And so he pointed out what are called finite element triples. So he pointed out that you need 3 things in order to have a finite element. And the 3 things are typically called K, P, and N. So K, which is in Rn, is the element's domain. And so there's a formal definition here, which I'm not going to write out because it's in your notes. It's a bounded closed set with non-empty interior and piecewise smooth boundary. So let's just quickly look at the ones that are in frequent use, right? So in one dimension, you've got one choice. It looks like an interval. In 2 dimensions, they're typically polygons, and the ones that overwhelmingly dominate are those 2. You can, in principle, produce finite elements on polygons that are not triangles or quads, but it is quite fiddly. So, as we'll see a bit later, there are special things about. So the special thing about the triangle is that the triangle is the simplex. So it's the point that is the figure you get by taking the lower dimensional shape, which is an interval, and adding 1 point. And that applies to a whole family. So the way you get a tetrahedron is you take a triangle and you add 1 point. And you can keep walking up through the spaces by doing that. And that's a special property which impacts on the way you can represent polynomials on that space. And these are special in a different way, because the cubes are the spaces you get by taking an interval and taking the tensor product with an interval. And then you can get a cube by taking the tensor product with another interval, and you can keep going up in that family like that. So these 2 families are kind of special, and therefore have advantageous properties, and therefore, both geometrically and also in the space. It's also easier to mesh using these things. And so therefore they dominate. And so in 3D, we get these ones, we get these ones, and as some of you in this room know, there is some call for an intermediate state, which is where you took so this one is the next triangle up. This one is achieved by taking a square and multiplying it by an interval. And you can do the intermediate thing. You can take a triangle multiplied by an interval and you get then a pie-shaped element. And that can be a clever idea if you have a very thin domain. So all the people in the room who look at atmosphere and ocean, where your domain is 1,000 times thinner than it is wide, that's a clever idea. Similarly, anyone who has an interest in studying metal shells, so if you're into the bodies of cars or aircraft or even the outsides of buildings and those sorts of things, then these sorts of elements can be advantageous in those circumstances. So that's what he means by the complicated statement. Bounded, so bounded was easy. Closed, okay, so closed just means that we include the boundary of it. Where are we? Set with non-empty interior, so we like to exclude the ones where the triangle has 0 height because that breaks all sorts of things for us. And piecewise smooth boundary, which you can see here, right? So that's quite important. So it's a relaxation on the strictest possible rule we could imagine, right? We can imagine a rule that said that you have to have a smooth boundary. But having a smooth boundary, that's not even a smooth boundary, makes it very, very difficult to glue these things together, right? It also, it turns out, makes it difficult to construct the polynomial spaces as well. But so it's actually a good thing that the requirement is only piecewise smooth. So we have smooth sections, and then we go around the corner and we have another smooth section. That's what piecewise smooth means in this context. Okay, so that's one of the 3 things that we need to have in order to have an element. Now, remember that the important thing about a finite element is that we can represent functions on it. That's the kind of the whole story. So we need P. So the reason I believe that he uses the term P for this is because the spaces we're thinking of are polynomial spaces, because almost exclusively those are what are used for finite element. But polynomial is not actually a requirement. What is a requirement is that this is a finite dimensional space of functions on K, and these are called the shape functions. So that's a finite dimensional function space. So that might, for example, be the linear polynomials, the quadratic polynomials, in more dimensions you can get more exotic about this. It can be the linear polynomials with the constraint that the normal component along an edge doesn't vary. That's called a Rabi-Thomas-zero element. That one will turn up later in the course. So you can have restrictions about what that space is, but it's a finite dimensional space. So we understood from our work on function spaces previously what that means. It means that we can write down a basis for that space, and that basis has a finite number, in fact then a fixed number of members, and that that number is what we call the dimension of the function space, right? And that dimension of the function space, the number of basis functions, is different from the dimension of the domain. So if I have one-dimensional domain and I have piecewise linear polynomials, then the basis happens to have 2 members. So that's a 2-dimensional function space. And then finally, what we need is n, which he writes in a complicated and curly way, which I'm going to have difficulty reproducing on the board. And n is a set of what are called the nodes of the elements. And so these are called the nodal variables, the nodes. And this is where that first half hour of this lecture comes in. These need to be a basis for P prime, or equivalently P star. So we bump into, at this point, the normal curse of mathematics, which is that mathematicians can't agree on the notation. And in the textbook, they have a subtle distinction, which we're not even going to walk near, about the difference between P prime and P star. And it turns out that in this particular context, the definition of the dual space that they labeled P prime is the one that we need. But the important thing is these things are in the dual space. And so having these will enable us to get a set of basis functions for the right polynomial space. That's how these things hang together. And as I point out here, so last time we worked out that the spaces that we solve finite element problems in are these solvable spaces, which are spaces with enough weak derivatives for the current purposes. So this thing is going to be in form a subspace of an appropriate Sobolev space, and so these things come from the dual space to the appropriate Sobolev space. There's a chicken and egg problem here, right? You use these things to define the things in here, so you can already know that. But that's fine. So this is where we get. So let's say that again. That's just the polynomial space that we're using, the set of functions we're using. I haven't yet written down a basis for that space. What I'm writing down is a basis for the dual of that space. So let's leap ahead of ourselves ever so slightly and understand why I wanted to write down this rather than just directly writing down my polynomial space and a basis for that polynomial space. And the reason is that we're used to thinking about elements, and the way we want to talk about elements and the way we want to reason about elements is by writing down, this is one of the few circumstances where it's easier to draw 2D than 1D. Let's write down a triangular element and say that I want to represent quadratic basis functions on that element. And so leaping ahead of myself slightly, I happen to know that I need to have 6 basis functions. And what I want to be able to say is that this element has basis functions which are given by that diagram. And that's a diagram which, if you've done some finite element, you look at that and you think you understand it. And if you were a finite difference person, you would say, oh, I really understand this. What it means is the unknowns in my problem are the values of this function at these points. And that's not quite the way that finite element people talk about this problem. So that is the intuition you have when you look at this. But really, when you solve a finite element problem, you're solving for the polynomials on this triangle. So the unknown is the polynomial function which is on this triangle. But those 6 points really still do mean something. And it turns out that those 6 points actually are effectively the basis of the dual space. Because if you define a quadratic finite element space by writing down these points, what you're actually saying is that I'm going to define as my nodes my polynomials evaluated at these points. And remember, those are functions. Evaluating the polynomial at this point and getting a number, the action of doing that is a functional. Right? There is a functional which says, given this point, evaluate the polynomial at it and get the number. That's what it means. And so these nodes are that. And the important point then is that given that you've decided how you'd like your nodes to be, you now need to recover a set of basis functions for these shape functions which do that. right? Let's say that again. I know which space I want to solve my problem in. I want to have quadratic functions. In order to solve the problem, I need to be able to write out all my quadratic functions in terms of an appropriate basis. And now I know something about that basis. I want that basis to have these nodes. So I know this space, and I know these nodes, and I need to use those two pieces of information to get back what the basis functions are that I wanted to solve. And so what we will do is we will write down the definition of that, and then we will have a brief break to allow that to settle in and allow me to get some caffeine. And then in the second half of the lecture, we'll actually use that to get out the values and see how this finite element construction thing works. For those of you who are Firedrake or Phoenix people, we are edging towards understanding what it is that Fiat actually does. We're not going to go into the guts of what Fiat does in this lecture course. That's actually a much more complicated question. But this is pretty much how Fiat works. Fiat works by the user setting up these things, and then Fiat works out for you automatically what the basis is. So that's the definition. Those three things there, if you write them out, define a finite element. So let K, P, N be a finite element. Then the basis phi 1, phi 2, all the way up to phi k of P, which is dual to N. So N is my set of nodes, and I'm going to tell you what dual to N means in a second. The space which is dual to N is called the nodal basis of P. Right? So this is a basis for P, and it's defined by being dual to N. And what it means to be dual to N is that, so remember N is a set of these things, and it means that Ni, so what's Ni? Ni is a functional. So Ni eats functions in P. So Ni of one of these basis functions, phi j, so I can take any one of these and any one of these, those are two different things, is equal to the Kronecker delta of I and j. So the Kronecker delta, that's the function 1, phi equals j, and 0 if I is not j. So what that means is that this is the set of polynomial functions, which each of which is 1 at one of the nodes. And so if our nodes are pointwise evaluation, that means it takes the value at that point. But we just saw earlier that our nodes could also be evaluation of a component, evaluation of the component of a derivative, the integral of the function over the domain, all those sorts of things could also be nodes. And what this means is that one of those functions evaluates that node to be 1, and all the other nodes are 0. So in the case of pointwise evaluation, that literally means that this function takes the value 1 at one of the nodes and 0 at all the other ones, and all the other basis functions take the value 0 at this point. That's what it means to be dual, and that's the important relationship between this dual space, the nodes, and the polynomial space, which enables you to get the polynomial basis functions having decided which nodes you want. So that is, I realize, if you haven't seen it before, quite hard. It's quite hard and deep. We're going to take a little bit of a break now. I'm going to get some coffee, and after that break, we will come back and do it practically for P1 on a one-dimensional interval and demonstrate how that actually works and that it actually falls out.